Hello, we're in Chapter 8 now, dealing with periodic properties. We just went through and talked about the quantum mechanical model of the atom. Now we're going to apply that model to some so what things about the periodic table. So if you remember, we talked about n, the principal quantum number, then L, the angular minimum quantum number. When L is 0, we have the s orbital 1 for L, the p orbital, angular minimum number 2 for the d orbital, and 3 for the f orbital. I mentioned about the Pauli exclusion principle. Oh, I said it again before. But let's start building up the electrons. So hydrogen has it's in its ground state, meaning its lowest energy state, has one electron in the 1s orbital. So we're showing this in the 1s orbital to spin up. And then helium, specifically what I mean by that with this 1s orbital, that n, the principal quantum number is 1, L is 0, magnetic quantum number is 0, and the spin is positive 1/2. It can be negative 1/2. It doesn't really matter. There's only one in the orbital right now. If you add a second electron in that orbital, it's going to be the same as the first, except it has spin down. And what that just means is the magnetic field of it, at any given time, it's in many different directions. The overall projection of it is in a specific direction, and it's just going to be opposite of the other one. We mentioned this before, that the Pauli exclusion principle, no two fermions can have the same set of quantum numbers in the same atoms. So, and the hydrogen atom, so all of the principal shells, so n equals 2, the 2s, 2p, same energy level. N equals 3, 3s, 3p, 3d. N equals 4, 4s, 4p, 4d, 4f. These are all the same energy levels. This is known as degenerates. So you're just a bunch of degenerates. I hope you are all a bunch of degenerates. I hope that you are all A+ awesome degenerates, uniform down to the T, right? That's what degenerate means. It means the same. Exactly. It usually has a negative connotation. You degenerates, all chewing your bubble gum and playing Cracker Jacks. So I don't know what they talk about in these. It's kind of an older word, right? So, that's the hydrogen atom, or hydrogen-like atoms. Hydrogen-like atoms have only one electron. Now, let's add one more electron in the mix, and what happens is that the electronic field and the magnetic field affect the electron energy levels. The effect that the electron energy levels have on the effect that the electric field has on the electron energy levels, this is known as a Stark effect. And then the magnetic field effect is called the Zeeman effect. The Zeeman effect is more specifically what causes the splitting. So splitting the electronic field, the Stark effect, is much more prominent in molecular orbitals. And I'm pretty bad at pop culture, but I saw the movie Iron Man when it came out, and when it was Tony Stark, at first I was like, oh yeah, just like the Stark effect. So I learned about the Stark effect before I learned about Iron Man. Anyways, let's go on and talk about Coulomb's law. Coulomb's law is the electronic field is equal to, actually it's just 1Q. Oh yeah, so the electronic field between two charges is 1 over 4 pi epsilon naught. Epsilon naught is a permittivity of free space. Q1, Q2, that's a charge of 1, charge of 2, over the distance between 1 and 2. The force acted on between them is the distance squared. So let's look at this. And the Coulombic force is what binds the atom together, electrons to the protons at least, or the positive nucleus. So, we talked this about shielding and penetration. So if you look at the lithium atom. Lithium has a +3 center. So, but there is a full shell of 2s electrons before that. The shield effectively shields the rest of the atom. And the other issue of that is that the other electron can penetrate a little bit through that, at least especially the s orbitals. So if you look here, if you look between the radial distribution of 2s and 2p, that's what the penetration is, so that the shielding does not have as much of an effect on the s orbitals as you do in the p's and the d's because of that penetration. But the real reason, the book tries to say that's the reason why the energy levels split. The real reason is because of the Zeeman effect. The Zeeman effect is what does that. So, all right, so this is where the energy levels split, and this is the non-hydrogen like atoms, and this is how they build up. So if you're going to build up electrons, so this is hydrogen, this is helium, this is lithium, this is beryllium, this is boron, and what do we do for nitrogen? The next thing is we can either go like this, spin up, spin down, or we can go like this. What happens is it goes like this, and the electrons have parallel spin. This is called Hund's rule. And then, so that's carbon, nitrogen, oxygen, fluorine, neon. So then the electrons, they build up like this. And Hund's rule sometimes is called the bus seat rule. And I don't like that. I like to swim laps. And I think of it more as the lap swimming lane rule because I love having my own lane when I swim. It's a rare joy when I can get my own lane swimming. So I'm swimming this way. And if someone wants to join me in the lane, what we tend to do is split the lane, and then we kind of, assuming we're even swimmers, I'll swim one way and he'll swim the other, or she. We don't. It's not a gender specific swimming pool. So, but the reason for this is that the electrons, they're negative and negatively charged. They don't like each other. Electrons do not like each other, and they will be as far away from each other as possible. So being in other orbitals is the better way. There is something called the pairing energy. When electrons pair, something called the pairing energy is released. It's very low for electrons. For protons and neutrons, that energy level is very high. And so even number of proton and even number of electron or neutron nuclei, the even ones tend to be much more stable than the odd. There are only a very few nuclei that are odd that are stable. And also for nuclear weapons, when you have an odd number of neutrons that are absorbed, then releasing the pairing energy, that is what gives it the activation energy to have a nuclear fission event. Okay, but electrons, not so strong. But so they pair up that way. That's the way they pair up. Okay, and the next thing we're going to talk about is paramagnetic and diamagnetic. This is different than ferromagnetic. There's only a few things that are ferromagnetic. Cobalt and iron are really it when it comes to this temperature, but at least of the elements. Paramagnetic means that there is one or more unpaired electron. We won't go into the difference between paramagnetic or ferromagnetic in this this class. Lithium is paramagnetic because it has one unpaired electron. Beryllium is diamagnetic. Boron is paramagnetic. Carbon is paramagnetic. Nitrogen is paramagnetic. Oxygen is paramagnetic. So is fluorine. Neon is not. So, and I want to be very clear on something. Whether or not something is paramagnetic or diamagnetic has nothing to do with its reactivity. Fluorine is paramagnetic. It's extremely reactive. Gold and platinum are both paramagnetic. It's extremely unreactive. So reactivity and diamagnetism. Also, calcium metal is diamagnetic. It's extremely reactive. Neon is very unreactive. It is not as diamagnetic. So there is nothing to do with reactivity. It's a common misconception. So let's see. What is the ground configuration for sodium? Couple things here. This 3s11, that breaks the Pauli exclusion principle. This one here, you can only have 6 in the p electrons shells, and I should say orbitals. You have 2 possibilities, this one and this one. These are both possible, but the thing is, the number D is an excited state, so it is, in fact, B. Excited state means it's higher energy. So, like I said, the party people doing jumping jacks versus lying down. So, the jumping jacks is excited state. Electrons are like humans, they want to be relaxed and low energy levels. And this is a bit early to introduce you to this, but I wanted to show you, this is the Lewis model. You've probably seen this before, the Lewis dot structure. If you go to UH Manoa, you can see Lewis's some of his notebook. I got my PhD from California, Berkeley, and Lewis was a professor there, and I got to see his notebook. It's really interesting. Lewis thought that atoms were like boxes, and boxes have 8 corners, and he thought that the 8 corners are the reason why that they were all that the number 8 configuration was so stable. And it's he was right about the 8. He was wrong about the reason. The reason for 8 is 2 electrons in the s orbital and then 6 in the p's. So 2 plus 6 is 8. The fact that it's like a box is just by chance. So it's a perfect correlation, but it has nothing to do with what reality is. So hydrogen and helium, they go for the 2. That when they bond, they go towards helium. And so noble gases, when atoms bond, they tend to go to the configuration of noble gases because it's particularly stable. So we talk about the octet rule, we're talking about Lewis structures, and this is a really extremely watered down version of the truth. The absolute truth is the reason why things bond together is that they're lower energy. And the energy levels that they form, if you look at the interactions between the electronic and magnetic field of the nuclei and the electrons, and as they interact, they'll form new molecular orbitals, and then the electrons will populate in those orbitals. If the electron energy levels that they form are lower energy from the bonding scheme than being alone, then the molecule might form depending on its shape, because sometimes forming the shape can be very hard. And also it depends on, with the shape, how the molecule can be turned and contorted. And certain molecules will only form in liquid phase versus vapor phase. Vapor phase, not many complex molecules will form. So that's the absolute truth. Now, but if I came at you with the math and said, okay, we're going to learn tons of calculus and math, and we're going to talk all about the complex conjugates, I would probably lose you, especially with a freshman, what's decidedly a freshman chemistry class. So these rules, they work very, very well, but they're models. They're not entirely true. Electrons are not dots. They're fuzzy packets of existence that we kind of know the position and momentum of. They're not dots. We know how much they weigh, at least in terms of their energy level. So we know that they're about 0.5 mega electron volts in terms of energy, and that's 9.11 times 10 to the minus 31 kilograms by mass. But that's for particle physics, oftentimes mass and energy are used interchangeably because they are equals mc squared, so you can get something's mass and energy if you want. Although, depending on how bound an electron is, its mass will actually change, or its apparent mass and apparent momentum, by how fast it's moving with its angular momentum, and also with its potential energy. So it's a complicated story. Okay, well let's go back down, and we'll go back to Lewis theory, where atoms are dots. And what's nice about this is it talks about the difference between valence electrons and core electrons. So I want you to look at this and think about valence electrons and core electrons. So hydrogen atom, neutral hydrogen atom is kind of like someone wearing a one-piece bathing suit. So bathing suit, nothing else on. Helium is kind of like someone wearing a bikini, like a top and a bottom. So wearing 2 articles of clothing, nothing else. So everything that you see is on the outside. Now lithium is like someone wearing bikini, top and a bottom, and then covering with a trench coat. So that outer electron covers, and you can't see what's on underneath. Then beryllium would be like a trench coat and a hat, and then you keep on adding more clothing. And then when you get to neon, then you put on a full body burqa, or get the sodium. That next electron is like a full body burqa that covers everything, and you can't see any other clothing that are underneath, and you start over fresh with a new shell. So think of it like that, like clothing. You can also, if you're a Shrek fan, atoms are like ogres. They're like onions. They're layered. This is the layers. This is the outer layers and the inner layers, just like an onion. Okay, and this specifically, so these dots correspond to these electronic structures, and this is known as the Aufbau, the building up principle. that's Aufbau, is build up in German. So Germany was the leader in science back in the when chemistry was in its formative years. Okay, write the electron configuration for germanium. Identify the valence electrons and the core electrons. Valence electrons are the highest and highest principal quantum shell only. So germanium is, okay, well, it's underneath silicon. So germanium, it's 1s squared, 2s squared, 2p squared, 3s squared, 3p squared. Then it goes 4s squared, 3d10, 4p germanium is 2, 4p 2. Okay, and we did the periodic table. Germanium is right here. And this is a configuration, and then the valence are right here. It has 4 valence electrons. It has the highest end. The 3d is not a valence electron. And why is this? The 3d is lower energy due to the Zeeman effect. And if you remember this chart here, you can see here that the 3d is, see, it's higher in energy than the 4s, but it's not considered to be valence. So actually the 4s electron is slightly further out from the nucleus than that. It's just it's the way energy works. If you have complaints about the way I'm doing this, you have to take it up with the creator, because or if there was a creator, I don't want to get into that argument. It's just the chemistry is a study of matter and its changes, and we're observing the way that matter interacts. So complaints need to go very high up in this category. Okay, so that's configuration. You wondered, how did I write that? Well, looking at the periodic table, so these are the s electrons, these are the p's, these are the d's, and these are the f's for the ground state. Now there are some exceptions to this rule. If you see, again, if you don't like this, take this up with someone much higher than myself, and you can also see there's no rhyme or reason. So iron has 4s squared 3d6, but now ruthenium goes up to 47. There's an exception there. That's weird. But then osmium goes right back to the way it was before. So copper, silver, and gold, these all go and they promote the 4s electron up into the full 3d shell. And these also tend to be very unreactive. So in general, those are the unreactive. And you can see platinum, palladium, they also promote their electrons. Nickel does not. But platinum, palladium, those are also they're called noble metals. They're unreactive. And that comes from the noble, because it's kind of a British term, like nobility. The commoners were fiery. They were the very fiery folk, but the nobles like, today is the happiest day of my life. And then say, today is the worst day of my life, because I'm noble and I'm unreactive. I'm not like a commoner. You can't tell me because I'm noble. That's the noble, means you're not reactive. You don't react. Noble metals. Okay. So, but this is the general trend that electrons build up in this fashion. The S's and the D's and the P's, and then these had different consequences. And okay, so let's do this. What is the electron configuration for selenium? Oh, and there's a shortcut. I should have gone this with germanium. There's a shortcut. We can just go and say, hey, you know what? This is argon's configuration. You can only do it for noble metals. You can't say, oh, this is zinc's configuration, so it's zinc 4p2. No, don't do it that way. It only works for noble gases. So you can do a shorthand that way. So selenium, you can give it argon's configuration, then for argon's configuration 4s2, 3d10, 4p4. 1, 2, 3, 4 for then selenium. So that's how you do it with the periodic table. And now next class we will talk about some of the consequences of the quantum mechanical model.